Dear colleagues, let us continue our session. Our next speaker is Alexander Katz with the report named Unreal AGMA star algebras of operators. Please, go.
Hello, can you hear me?
Yes.
Okay. Hello, everyone. Thank you for the opportunity to being able to deliver a talk at your conference. And greetings from New York. So my talk is on the real sigma star algebras of operators. So what is it all about? Well, let us first look at the complex Hilbert space and a set of bounded operators there. A subset of B of H sub C is called sigma closed if given any sequence which converges to an operator in B of H sub C in the weak operator topology that implies that the limit does belong to S as well. So if you're now going to look at any set, a subset of B of H sub C, obviously there is the smallest sigma closed set, let's call it sigma of S, containing it. We can take just a theoretical intersection of all those. Right? So this creature, this class of object sigma star algebras of operators were introduced and initially studied in the 60s, actually paper appeared in 68 by Davis to be sequentially weakly closed C-star algebras of operators in a complex Hilbert space. Thus, what was required is that the algebra itself is equal to its sigma envelope. Kedison, the Kedison appendix to the same paper have given conditions under which a sigma star algebra is actually weakly closed, means a von Neumann algebra. Indeed, to summarize the main results of this paper of Davis with appendix of Kedison, they got the follows. That if B is a C-star algebra of operators on a complex Hilbert space, then the following statements are valid. A sigma envelope of an algebra is an operator sigma star algebra. If B is separable, non-separable, I mean, sigma of B is unital. If a Hilbert space is separable, then its sigma envelope coincides with the smallest von Neumann algebra, B commutant of B generated by B. And finally, if the center of the bicommutant of B is countably decomposable and B is non-separable, then the sigma envelope coincides with B commutant. So this theorem is a starting point, and also a few words needs to be needed. Why it is all needed? Well, as you probably know, C-star algebras and von Neumann algebras were used to solve one of the Hilbert problems mentioned in his Erlangen program of give axiomatization for physics. And ideally, we're looking for a possibility to have objects that would be models for both classical mechanics and quantum mechanics. The problem is that if we're going to use von Neumann algebra, it's not really satisfying that condition. Indeed, using sigma star algebras approach and Kedison's definition of dynamic systems, Plyman in the same year, 1968, modified Mackey's axioms for quantum mechanics, obtaining 8 axioms, which we call the essential axioms of Mackey. He actually changed 2 of them to drop another. For instance, instead of requiring the existence of an observable corresponding to any real valued Borel function of a given observable Marquis axiom 3, those require the correspondence only for bounded Borel functions. And this is important because that would mean that this approach with sigma star algebras would include classical statistical mechanics, whereas the von Neumann algebra approach excludes this case. One can refer to a monograph by Gerard Remb, published in 1972, of algebraic approaches to statistical physics and field theory for further elaboration on the topic. Right? Now, since we are looking for models to realize quantum mechanics, it is important for us to find some nice classes of algebras between C-star algebras and von Neumann algebras, being more restrictive than C-star algebras, but not as restrictive as for Neumann algebra, so that the meaningful physics can be there. And in fact, according to von Neumann approach, since observable are realized by self-adjoint operators, we are basically focusing on self-adjoint parts of these associative star algebras, so-called Jordan algebras. They are not closed under associative multiplication, but rather closed under symmetric Jordan multiplication, like IB plus B over 2. In the case of normed algebras, these are so-called JC algebras. For example, if you're going to take a C-star algebra and replace the original associative multiplication by symmetrized multiplication, AB plus B over 2, we get so-called JC algebra. But since on one hand, self-adjoint part of a complex C-star algebra is a JC algebra, but not all self-adjoint parts of real C-star algebras are JC algebras, which can be realized or represented as self-adjoint parts of complex C-star algebras. You can refer to work of Sturmer published in late 60s. It is interesting, therefore, and important for physical considerations to study real analogies of sigma star algebras. And here we begin this investigation, and this will be one in a series of publications related to that topic. So first, for the listeners to understand what's going on and what is the purpose and the difference of a complex case versus real case, let us discuss some specifics of first operators on a real Hilbert space. So let us recall some basic facts. So if H is a real Hilbert space with an inner product, here, right? And the corresponding norm generated by the inner product. Then if we're going to take a complexification of H to be then the natural inner product of complexification then can be given by the following form. And one can check that it is indeed a complex inner product in a complexification of a real Hilbert space. Now, let us also introduce a conjugation to be the following for any form of vectors x plus iy. If we turn it to x minus iy, it's going to be a real linear isomorphism of h sub c, whose square is equal to identity. Right? So now if we denote by b of h the real algebra of all bounded are linear operators acting on A, similarly, when we take the complexification, we denote the complex algebra consisting of all bounded C-linear operators acting on complexification. And for an arbitrary operator that belongs to the complex Hilbert space operators, we denote by sigma of S, its natural spectrum. Each operator in real on real Hilbert space has a natural extension to an operator on a complex Hilbert space, which is given simply by linearity. But notice that this is an operator that's acting on complexification, and this is the operator that's acting on the real Hilbert space. Moreover, if you're going to look at that map that puts in a correspondence T with T sub C, whereas T belongs to B of H and T sub C belongs to B of H sub C, it is unital, R linear, adjective, and multiplicative, right? In particular, an operator of B of H is invertible if and only if its complex extension is invertible. The operator T sub C will be sometimes called the complex extension of the real operator T. Right? If we're going to fix an operator S in a complex on a complex Hilbert space, we can define an operator of S super sigma to be equal to that triple product. We multiply S from the left and from the right by conjugacy. It is easily seen that this correspondence from S to S super C is a unital conjugate linear automorphism whose square is the identity of B of H sub C. And because if we're going to take all fixed points on the conjugation, we have that S super sigma is simply equal to S if and only if S leaves the real part when it is embedded into H super C fixed. In this case, a restriction, if we're gonna take a restriction of S on H and make that sub C thing, we're gonna get the following, that, oops, I'm sorry, that T sub C super sigma is simply equal to T sub C, means super sigma leaves T sub C invariant under its action for all operators T from the real Hilbert space operators B of H, right? In fact, because the following representation is given where S plus S super C acting on the whole real Hilbert space belongs to the same real Hilbert space. And if we multiply the difference of this action, act on H with multiplication by a complex identity, it's also going to belong to H. So the algebras B of H sub C and B of H sub C means here by sub C, we means that we switch from each operator T to operator T sub C. It's going to be isomorphic. And that's why we can identify them. In other words, the algebra B of H, right, may be and will be regarded as a real subalgebra of an algebra B of H sub C. In particular, if we represent an operator as a sum of its real and imaginary part with U and V from real B of H, we have that S super sigma is going to be then U minus IV. So the map from S to F super sigma is a good conjugation of the complex algebra B of H sub C induced by conjugation C on a complex Hilbert space. For an operator T from B of H real acting on the real Hilbert space, we denote by its Hilbert space adjoint, the usual thing, right? For X and Y from H. And as we have when we apply the conjugation on the complexification for the operator T, it's easily seen that the conjugation of T sub C is a sub C of conjugation. and this operator will be simply denoted therefore by C sub C conjugate. Moreover, if we use the super sigma operator, then we have C sub C conjugate super sigma is equal to T sub C conjugate, means super sigma leaves it invariant, right? So the real counterparts of complex C-star algebras, so-called real C-star algebras, were perhaps first mentioned by Ingelstam, who studied real Banach algebras in 1960. He actually crafted the name for them. And they've since been studied by many authors, and there's literature where they're mentioned along with complex algebras, but there are also a few books dedicated specifically to real C-star algebras. So there are a few equivalent definitions. One of them would be, for example, that a real C-star algebra is a Banach star algebra, real Banach star algebra, which is isometrically star isomorphic to a norm-closed star algebra of bounded linear operators on a real Hilbert space. An equivalent abstract definition would be that the real C-star algebra is a real Banach star algebra satisfying the usual C-star regularity identity on the norm, and having the property that for all elements, the positive element A star A has spectrums that contain in from 0 to plus infinity, or equivalently having the following inequality for norm. You cannot drop this condition for real C-star algebras, though even it was included in the original definition by Gelfand and Nyberg. It was later found superficious in a complex case, right? So given a real C-star algebra, its complexification A sub C is a C-star algebra complex and comes with a real linear automorphism sigma, which square is equal to identity, namely complex conjugation with having A fixed under this operation. Alternatively, we can consider the following. We can define theta of A being sigma of a conjugate, which is otherwise speaking a conjugation of sigma of A. Then due to that star applied, theta is going to be complex linear star anti-automorphism of a complexification which square is equal to identity. Thus, we can classify real C-star algebras by classifying their complexification and then classifying all possibilities for sigma or theta. This raises a number of questions, in particular, given a complex C-star algebra. Is it that the complexification of real C-star algebra? Equivalently, does it admit an anti-automorphism which square is equal to identity? The answer to that is no. For example, in 1975, Kohn published his famous papers that's called an example of factor not anti-isomorphic to itself, where he gave an example of von Neumann factor acting on a complex Hilbert space that doesn't have any anti-automorphism. Thus, not all complex algebras can be obtained as complexification of real algebras, means it's not the same thing. Now let us turn to von Neumann story, von Neumann algebra story. Real von Neumann algebras were studied systematically by Sturmer in the same already mentioned papers in 60s. They're closely related to complex von Neumann algebras with involutory star antimorphism in the same manner like it was already mentioned on the previous slide. Through this relation, much of the structure theory of von Neumann algebras, for example, the type classification and integral decomposition into factors, can be transferred to the real case. That program was undertaken by a number of authors, to name a few, Yupov, Lee, and some others. So by definition, a real von Neumann algebra is a unital weakly closed real self-adjoint subalgebra of the real algebra bounded linear operators on a complex Hilbert space with the property that it intersects with its minimification by only zero operator. Equivalently, let H be a real Hilbert space as Tassar algebra M sub R of the algebra B of H of all bounded real linear operators on H is a real von Neumann algebra if it satisfies the von Neumann Bikumentant theorem, means it coincides with its Bikumentant taking within B of H. It is equivalent to M sub R being weakly closed real star subalgebra of real B of H, and M sub R being dual space of a real Banach space, which is pre-dual to it, like equivalent to Sakai definition of W star algebras. So let now H sub C is a complexification of a real Hilbert space. And let's take a real von Neumann algebra in B of H. Then complexification M would belong to B of complexification of H. And then we notice the following: that the commutant of M acting on B of H sub C will be a complexification of commutants of M sub R taken in B of H, and sorry, this is double. That's omission. And a double commutant will be a complexification of double commutants. Therefore, M sub R is a real von Neumann algebra on H if and only if its complexification will be a complex von Neumann algebra on complexification of H. Here are a few basic facts about complex von Neumann algebras, including the ones that I have already mentioned. But what is important? What is important is the follows: that indeed a real von Neumann algebra is split in a sum of symmetric and anti-symmetric element, and its self-adjoint part is not generating it as a whole, unlike the complex case where each element can be uniquely represented as a finite sum of as a linear combination of self-adjoint part. So here the generating part will be symmetric and anti-symmetric, which creates a totally different story, with physics being contained in a symmetric part and anti-symmetric part being a Lie algebra, in fact, with Poisson bracket. Now let us turn to what is being done here. We're trying to define a real analogy of complex sigma star algebra. So let's S sub R be bounded linear, a set of bounded linear operators on a real Hilbert space. We're going to call it sigma sub R closed in the same way like Davis defined sigma closeness for the complex case, means if it is closed in a weak operator topology of H sub R. And then we take sigma sub R of S sub R being intersection of all of those. Then the following lemma is valid, that if S is any such set, and we take its complexification and the complexification of the real Hilbert space, then if we look at these envelopes, then the complexification of real envelopes will be a complex envelope. This is an important lemma because it allows us to transfer from real case to complex case through complexification, and this intersection of taking sigma envelopes with complexification. So we're talking about like commutation of diagrams, right? So now to be able to use this machinery, we define a real analogy of a complex sigma star algebras as follows. A real C-star algebra of real linear operators on a real Hilbert space is called the real sigma star algebra of operators if its complexification will be a complex sigma star algebra on a complexification of Hilbert spaces. Right, and then the following theorem is needed for our apparatus. Let's A be a real C-star algebra of real linear operators on a real Hilbert space. Then it's going to be a real sigma star algebra of operators if and only if the sigma envelope of its complexification is equal to a complexification of its sigma envelopes. And then as a result, we obtain the following generalization or extension to the real case of theorem of Davis and Cadison. If A be a real C-star algebra of operators acting on a real Hilbert space H, then the following statements will be valid. It's a sigma envelope in a real B of H. It's going to be a real operator algebra. It's not immediately obvious that when you take an algebra and you take its envelope, it's again algebra. You have to check that all axioms fly with sequential weak closure. Second, if A is separable, non-separable, I mean, then its sigma closure will be unital. Generally speaking, sigma star algebras in a complex and real case do not possess identity, unlike von Neumann algebras. If you take, like, say, B commutant of any C-star algebra, you immediately get that identity is there. It's not the case with sigma envelopes. Third, if H is separable, then its sigma closure coincides with the real von Neumann algebra B commutant generated by A inside the real B of H. And finally, if center of B commutant is countably decomposable inside real B of H, and then an A is norm separable, then the sigma closure coincides with B commutant. So you can see that we got basically the correspondence for each of the main results from the paper of Davis and appendix by Cadison, the key results, and we obtained that through the technique of complexification for which technical lemata were developed. Here is the list of references, which includes this original paper of Davis published in '68 in Communication Mathematical Physics on barrel structure of C-star algebras. This is the paper of Kohn that I have mentioned, which gives an example of a von Neumann algebra that doesn't have any star anti-automorphisms on it. This is the original paper of Ingelstam, where real C-star algebras was first mentioned. This monograph of Ayub Frahimov-Usmanov give you basic ideas of Jordan real and Lie structure in operator algebras like C-star and von Neumann algebras. That book of Lie is dedicated to real operator algebras. This is one of the key papers of Lie, where he developed the theory of real C-star algebras, real von Neumann algebras. This is a classic reference for C-star von Neumann algebra theory. This is the Plyman's paper, where he elaborates on Davis paper and applies it to modify Marquis axioms to use sigma star algebras instead of von Neumann algebras for quantum physics axiomatization. This is a nice review of structure and applications of real C-star algebras by Jonathan Rosenberg, and these are this classical work of Sturmer in late 60s, where he basically defined JC algebras, real C-star, real von Neumann algebras. And that's the end of my talk, and thank you very much for your attention.
Thank you very much.